Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.1. Areas and Riemann sums.
Lesson 1. The right and left hand rules. Part 2.
We could try exactly the same process, but instead of having 4 strips, we could break it up into 8 strips. So let's think about that. We're still doing the interval from 0 to 8, and we're now going to break it up into 8 different strips. So how wide is each strip going to be? What will that little delta x width be equal to? It looks like each one will be 1 unit, and there is a little formula that you can use to figure out how wide each strip is. We just take the end point over here, I'll call that B in general, and the beginning point that we're starting at, I'll call that A. So those are the x values that go from the beginning to the end of our region. We divide it by the number of strips that we're going to break that region up into. So in our case, we're going from 0 to 8. So my A value is 0 and my B value is 8, and I'm going to be dividing it into 8 different rectangles, so I get 8 over 8, or 1 for the width of each strip. Or you can just draw the picture and see that this width is clearly equal to 1 unit, as it is for all of these rectangles. Okay, well, now let's go ahead and see if we can find what we would call r sub 8. So that would be, since I have an r here, that would be using the right hand endpoints to create the height of each of my rectangles. So for example, on the first strip, I'm going now from 0 to 1, and I want to choose the right hand endpoint to evaluate my height at. That would be an x value of 1. And so the rectangle that I end up getting would have the same height as this green height underneath the curve, and I would get a rectangle that looks something like this for my very first rectangle. Well, I'd like you to pause the video and see if you can figure out the same kind of sum that we did before. You'll need to figure out what the height here is, so you have to figure out how to find that height. And remember, for the first rectangle, you're just going to take this green height, multiply by the width, which we decided already is 1, and that'll give you the area of your first approximating rectangle. So try to figure out, in this case you're going to have 8 different approximating rectangles. Try to go ahead and figure out what those are. What the areas of all of those are, and also draw the picture and be sure that you are using the right hand endpoint in each case to figure out the height underneath the graph. If you get done with that and you feel confident, you can go on and try doing the same thing with the left hand endpoints. Try to draw the picture and also figure out the areas of the 8 rectangles that you'll end up getting. And you might again ask yourself the question, is the estimate that you end up with, R8, the sum of those areas, is that too large or too small? And the same thing with L8. Is the estimate that you get here too large or too small? And you could also compare them with R4 and L4 and see if you feel like we are getting something that's closer to the true area under the graph. And then we'll go through all of this page together. Okay, well, let's go ahead and work on trying to find the area of this first rectangle. We need to find what the height is here, and remember that we just need to find the value of our function at this x value, an x value of 1, so we'd be finding f of 1, where f of x in general is square root of x. So if I want f of 1, that would just be equal to square root of 1, which is 1. So the height of my first rectangle would be a height of, I'm going to write it as root 1. And the width now is just 1 unit, So the width is equal to 1. So the area of my first rectangle will be root 1 times 1, or if you wanted to simplify it, it would just be the number 1. Let's go to the second rectangle. I look at the second strip. I choose the right-hand endpoint for the height of my rectangle on the second strip. So I'm going to be using this green line, this green height underneath the curve to create my rectangle. So I make a rectangle that is that high, the height of that green line. So my second rectangle would look something like this. And if I want to answer the question, well, how high is that? What is the height of that second rectangle? I would just go ahead and figure out what my function value is at this x value. So that would be f of 2, which is root 2. So my second rectangle will have a height of root 2, and its width is still equal to 1. All the rectangles have a width of 1. So if we're simplifying down here, we now have 1 plus root 2. And I just continue to do that. So you notice that for the third rectangle, I'm going to choose 3. That's the right-hand endpoint of that strip. I make a rectangle that's as high as this green segment is under the curve at the value x equals 3. My third rectangle will look like this. And what's the height of that rectangle? Well, it's just going to be f evaluated at 3. And for this function, that would be square root of 3. So my next rectangle will be root 3 times 1, or root 3. Well, I think you can probably start to see that there's a pattern here, so you might not have to think quite so hard for every single one of these rectangles. I'm going to go ahead and draw the picture in of the other rectangles because I asked you to do that. So here are my other approximating purple rectangles, and you can probably notice that the first rectangle had a height of root 1, the second root 2, the third root 3. The fourth one will have a height of root 4 times 1. If you want to simplify that, that would be 2. The next one would be a height of root 5 times a width of 1, or root 5, and so on. I'd have a root 6 times 1, or root 6 if you want to simplify, a root 7 times 1 for the 7th, and the very last one, I always sort of like to double check that I'm doing it correctly and I'm stopping where I'm supposed to if I use this system. The very last one, the height is right here, and I can see that that would be, put my arrow on there, that would be f evaluated at an x value of 8, so that would be root 8. So my very last rectangle would be root 8 times 1. Or if you want to simplify that to root 2. So that's going to be R8. That's the sum of the areas of those purple rectangles. And what does that come out to be? I found on a calculator that this comes out to be equal to approximately 16.306000053. So it's 16.3 roughly. Well, if you went ahead and looked at the same thing with the left-hand endpoints, but now again with 8 rectangles instead of with what we originally had, 4 rectangles, you notice that the widths will still be the same as they were for our R8. The width of each of these strips is still equal to 1. But when we look at our first strip and decide where to look for the height underneath the curve, we're now supposed to use the left-hand endpoint of that interval. So I go from 0 to 1, I want to use the left-hand endpoint. That would be right here at 0, which means that if I plug 0 into my function, f of 0 would be square root of 0, or 0. So this rectangle has a height of 0. So I don't go up at all to create my rectangle. And again, it's really just a line segment. It's a rectangle that has, we say it's degenerated into just a line segment. So the area of this first rectangle is going to be 0. It's really square root of 0 that's the height, times the width, which is 1. So if you simplified, you'd end up getting 0 there. Well, let's go to our next strip. Again, I want to choose the left-hand endpoint, so I'm looking at the interval from 1 to 2. I'm going to choose 1. I look at the height under the curve at x equal 1, so I'm going to be using this green height to create my rectangle, and I make a rectangle that is that high. So my second rectangle will look like this, and if I want to figure out, well, what is the height of that second rectangle, notice that you're just doing f evaluated at 1, so it would be square root of 1, or 1 if you want to simplify it. So the second rectangle will be square root of 1 times its width, which is again 1 unit width, so I would end up with 1 if I want to simplify that. Well, we continue this process just as we did for the rectangles that used the right-hand endpoint for the heights. Here's my third rectangle. I want to use the left-hand endpoint, so I'm looking at x equal 2, and I've created a rectangle that is that high, the green height under the curve. And if I want to know how high is that, again, I just do f evaluated at this x value, at x equal 2, and I get root 2. So my third rectangle would have a height of root 2 and a width of 1. And again, you can probably start to see that there's a pattern there. So you might not have to think out every single rectangle, but I'm going to draw the picture so that we can see it and kind of compare it to what we had when we had L4 instead of L8. And you notice that for each rectangle, I'm making the rectangle as high as the left-hand side of that strip. And just for a check, let's just check the very last one. The last one's going to have a height at the left-hand side, so we want this green height under the curve. That's at an x value of 7. So to find this height, I just plug 7 into my function, and I would get square root of 7. So that's the height of the last rectangle. And so I'm going to have root 0 times 1 plus root 1 times 1 plus root 2 times 1. The next one would be root 3 times 1, and so on. Root 4 times 1, root 5 times 1, root 6 times 1. And the very last rectangle, since we're using the left-hand sides of each strip for the height, is root 7 times 1. And if you want to, you can simplify that and add it up. It's root 2 plus root 3 plus root 4 plus root 5 plus root 6 plus root 7. And I put that into a calculator to get an approximation. It turns out to be 13.475734. So here was our value for R8, and down here is our value for L8. And one thing you might notice is that these two numbers are closer together than the R4 and the L4 that we had. If we compare, first of all, R4, you notice we said that was too big. We could see that that hung over the actual curve. It was 17.38. And we compare that to R8, it's 16.3 something. So we're suspecting that this 16.3 is a better approximation than 17.3. The area that we know that is too large, this area, R8, we can see that L8 is going to be too small, but these two values are closer together. So I'm guessing that 16.3 is a better approximation to the true area under the curve than 17.38 was. And that turns out indeed to be true. You can even see it if you compare sort of how much air we have. That's what's hanging over the curve. It looks a lot bigger, like the total of these chunks that are hanging above the black curve is quite a bit larger than the total error that we have in this picture, which is just these little bits that are hanging above the black curve. So as we go to more rectangles, we are getting something that is closer in an approximation to the true area under the curve. Same thing with L4 and L8. Here was our L4, and we said that was 11.72. Now we're up to 13.47, so we suspect that this is a lot closer to the true area. And if you look at the error, which would really be how much too small this is, it's these white areas in here that we're missing. That's a lot of white area. If you were to add all that up, that's the error in this approximation for L4. And there's a lot less white space here. These are our errors in this case, are these little white chunks that we haven't counted in our approximation for L8. So I can see that this is going to be quite a bit better than L4 was. And of course, if we averaged these two, you would get something that's even closer. I think I did that. The average of L8 and R8 turns out to be, just for your information, 14.89178697 if you want all of the digits on my calculator. And so that's our new average. And that is indeed a lot closer to the true area. So our average of R4 and L4 was 14.5 something, and this is 14.9 something if we round to the nearest tenths. So those approximations are quite a bit better. Oh, before we leave this page, one other thing that I want to mention about what happens when you average the right-hand endpoint estimate and the left-hand endpoint estimate, as we did here for R4 and L4. So we added those together and divided by 2. This is actually the same as another technique for figuring out an estimate of the area under a curve, and you'll learn about that next semester. It's called the trapezoid rule, where instead of using rectangles as we are here, you actually use a little trapezoid on each of your strips, and that turns out to be a very efficient way to estimate the area under the curve. But when we average R4 and L4, we end up with something that's the same as what you would get using trapezoids instead of using rectangles on each of these strips to estimate the area. So that's just a little side note. You'll learn about the trapezoid rule along with other rules such as Simpson's rule, which are more efficient than what we are doing in this semester. Well, what would be still more accurate than what we have done so far? Okay, so that's the next question. Could I make my estimates even better? And of course we said you could average L8 and R8 together. You get a better estimate that way. It's really the same as the trapezoid rule that you'll learn about next semester. But to get more accurate still, what could I do? I could increase again the number of rectangles. So in this picture, I've actually got my number of rectangles up to 16. So now I'm going to look at n equals 16 rectangles. And I don't necessarily have to just double it. I could make it 10 rectangles or something like that. That would still be better than 8 rectangles. But doubling things is a fairly easy thing to do computationally. Okay, so let's try figuring out R16 and L16. In other words, we'll figure out the sum of the rectangles that use the right-hand side of each strip in order to create the height of the rectangle, and then we'll do the sum of the rectangles where we use the left-hand side of each strip in order to figure out how high each rectangle is. And I won't go through these in as much detail as we did the others, but let's go ahead and at least see if we can figure out for n equals 16 what the width of each of these rectangles is going to be. You might be able to tell just from the picture, we're splitting it up into twice as many rectangles as L8 and R8. So since those had a width of 1, you're probably guessing, oh yeah, now I'm going to have a width that is just 0.5. It's just half of a unit, and that's correct. Or you can use our little formula, delta x, which is the width of each of our approximating rectangles, is b minus a over n, where b and a are your endpoints of the total interval that you're looking for the area under the curve on. So we said b is equal to 8 and a is equal to 0, and now we're breaking it into 16 rectangles, so you can see that reduces to 1/2 or 0.5. So now each strip is only a half a unit long. Okay, so if you were figuring out R16, let's see if we can do that. Let me put my function in here also. F of x is square root of x. That's the function we're trying to find the area underneath. So R16, we're going to have 16 of these rectangles, and that's what I drew the picture for, and I drew it for us because it just takes a long time to draw that each time. So R16, well, I'm going to need the height on this first subinterval, and where will this first subinterval end? I'm going from 0, I'm going 0.5 units to the right, so it's going to end here at 0.5. I'd put 0.5, but it's just hard to squeeze that in there. And you notice the next rectangle is 0.5 units to the right of that, so that ends at 1. The next rectangle is 0.5 units to the right of that, so where will that end? It will end at 1.5, and so on. Another half unit, I get to 2. Another half unit, I get to 2.5. 3, 3.5, 4, 4.5, and so on, all the way up to 7, 7.5, 8. I won't write all the ones in between. Okay, so let's see if we can write down what R16 would be. Well, when I look at this first rectangle, I'm using the right-hand side, the right-hand endpoint, to evaluate the height of that rectangle. So the very first rectangle would end up having a height of f evaluated at 0.5. In other words, it'll be square root of 0.5. So my very first rectangle for R16 will have a height of square root of, I'll just put 0.5 in there to save space, and then I multiply by the width of my rectangle. The width is now 0.5, so I multiply by 0.5. Again, I'm just going to write that as 0.5 to save some space. For the second rectangle, we do exactly the same thing, and I can see that the height of the second rectangle, I'm going to the right-hand endpoint, will be f evaluated at 1, so that'll be square root of 1. So my second rectangle would be square root of 1 times my width, and the widths are all 0.5. Third rectangle, I think we can start to see the pattern, is going to be the height at this right endpoint, so that's going to be at 1.5, so I'll have square root of 1.5 times its width of 0.5. The next one will be square root of 2, that's the next subinterval value I have there, times 0.5, and so on. And I keep adding all of these up until I get to the very last rectangle, and I always like to double check to be sure that I'm ending at the right place. The very last rectangle, if I'm using the right hand endpoint, I'm going to be using 8, so I would have f of 8, or square root of 8. So the very last rectangle would be root 8, and then I'd multiply by the width of 0.5. Well, I think I went ahead and figured out what this is approximately equal to, and it's roughly equal to 15.7222 something. That's probably close enough. L16, well, that just means I'm going to use the left-hand endpoint of all these subintervals. So instead of having all of these values, the 0.5, and then you notice the next rectangle was, I was taking square root of 1, and then square root of 1.5, square root of 2, and so on, all the way up to the last right-hand endpoint, root 8. For the left-hand side, I'm just going to be using the x value at the left of each subinterval. So instead of starting at 0.5, the right side, I start at 0, the left-hand side. So my very first rectangle would be root 0, and then I multiply by the width. The next one will be the next subinterval value, so it'll be square root of 0.5, and I multiply by the width. And the next one, I'm using the left-hand endpoint. We're now on the third strip, and so I would use root 1 times 0.5, and so on. I keep doing that until I get to the very last rectangle. If I'm using the left-hand endpoint, then for the very last rectangle, I'm using the height at 7.5 rather than the height at 8. So I would do f of 7.5, and for this function that'd be square root of 7.5. So for the very last one, it would be square root of 7.5 times 0.5. So for the left hand estimate, I just kind of shift everything one to the left, and instead of starting at 0.5 and doing the square root of this number, square root of this number, square root of this number, I start at 0 and do the square root of this number, square root of this number. It's just everything's shifted to the left by a half a unit. And instead of ending at 8 as I did for the right hand estimate, I end at 7.5. So I hope that makes sense. If not, just write out the details yourself and make sure that it makes sense in your own mind. So I plugged L16 into this estimate that I have written down here into a calculator, and I got 14.30802 something. So the right hand estimate with 16 rectangles is this. The left hand estimate with 16 rectangles is this, and you can see that these are getting a lot closer together. If we compare it to what we had with R8 and L8, you notice this was, R8 was 16.3 and L8 was 13.4, so those are about 3 units apart, whereas these are only, about less than a unit and a half apart. So these are quite a bit closer to each other. Okay, well, you can do this same thing and keep increasing the number of rectangles. I doubled them. You don't have to double them. And actually, I had a little program that somebody gave me for my TI-84 Plus. It's an old calculator. I used that to add all these things up because it's very laborious to go through and add these things by hand on a calculator, but it's super simple to program your calculator to do these calculations for you. And somebody did that and gave me their little program, so that was terrific. Or you can use Mathematica, it will do the same thing for you. And so I just went ahead and plugged it into my calculator. You just give it the number of rectangles and you tell it what function to use and what your A value is. That was 0, that's the left-hand endpoint, and your B value is the right-hand endpoint, so that was 8, and it just does it for you. So R32 turned out to be 15.4134 something, and L32 turned out to be 14.7063, and then there were some more digits there. And you can see that these are even closer together, and so we have confidence that we're kind of narrowing in on the true area by increasing the number of rectangles. By the way, it took my TI-84 Plus calculator 2 seconds to compute this. So it's actually a lot of computations to figure out R32 and L32. You're figuring out the areas of 32 rectangles for each of those, and I put it in the information and the number of rectangles and so on in there and hit the button, and for each of these it took about 2 seconds. I decided to jump ahead and I made n the number of rectangles 1024, so I doubled these a few times and got down to 1024, and since I had a program to do it, I wasn't going to add up the areas of 1024 rectangles myself, but my program did it for me. And for the right hand endpoint I got 15.9585 something, and for the left hand endpoint I got 15.07, this is a 9 here, 0.7375 something. And you can see that these two are really close together. And so we're guessing that the true area, we know this is an overestimate and this is an underestimate. So the true area has to be somewhere between 15.095 and 15.073. So the true area, we're getting a very accurate idea of what it is. However, it takes a lot more calculating time, and it actually took my TI 84 Plus, it took it 90 seconds to do each one of these. So you can tell that there's a lot of calculating that's going on in there. If you were to average these two together, you get a very accurate estimate for the true green area under the curve. And the average, which would be the same as using the trap rule, we call it the trapezoidal rule, the average of these two turns out to be 15.0848098. And that, we're guessing, is pretty close to the true area. Well, it happens that I know what the exact true area is, and let me tell you what that turns out to be. It turns out that the true area, just so that we can compare it, the true area, this pen doesn't want to work. Turns out to be the following. I'll put it right underneath this so we can compare. It's 15.0849447, and actually it's an infinite decimal expansion, so I'll put ... there. But you can see that when we go up to 1024 rectangles, we're pretty darn close to what the true area under the curve is. In fact, here's the tenths column, the hundredths column, the thousands column. They don't differ until I get way out here to the 10,000ths column. So our estimate was actually accurate to the nearest thousandth of a unit. So this is a good, I'll say very good, approximation. But it is not the exact area under the curve. And so that's a great approximation. Of course, you can continue to increase the number of rectangles and get more and more rectangles, do more and more calculations, get closer and closer to the true area. I can see even with 16 rectangles, it looks like the error is getting quite small. These rectangles are fitting very much closer to the actual area that would be underneath the curve. But my question down here at the bottom is this. Is there a way to use this method, adding up areas of rectangles, to get the exact area under the curve? I said the true area was this number in red, the 15.0849447 ... I said this is the exact area under the curve. I didn't even tell you how I found that exact area. It's a secret that you will learn about in the next section. So that's that magical, wonderful theorem that I alluded to at the end of the previous video and the beginning of this one. But is there a way to use the method we've been discussing to find the exact area under the curve? What would you have to do? Well, let's think about it. If I use more rectangles, I get a better approximation. We know that. How many rectangles do I have to use to get the exact area under the curve? Now, you've probably guessed it. Let the number of rectangles n, we want it to get larger and larger, but to get the exact area, what would we have to do? We would have to let n go to infinity. If we could somehow let the number of rectangles go to infinity, we would have the exact area under the curve. What does that mean about the width of each rectangle, delta x, if the number of rectangles is going to infinity? Well, if you divide it up into more and more rectangles, the rectangles are getting skinnier and skinnier. And here I drew sort of a picture with a whole lot of rectangles. Of course, it's not an infinite number. And I kind of drew it by hand because I had to use a thin pen to try to get the rectangles in there. My fat pens are too fat. So the width of these rectangles, what's happening to the width of each of these tiny little rectangles, the rectangles are getting skinnier and skinnier as we increase the number that we're packing into this interval from 0 to 8. And so the width of each rectangle will be going towards 0. So the rectangles get skinnier and skinnier, the number increases more and more, and you can see that in this picture where I have a whole lot of rectangles, I didn't even count how many there are, but you can see that the error, the amount that these rectangles hang over, you probably can't even see it on the video, that there's some very fine lines here that show that the rectangles still stick up over the top of the y = root x curve a little bit, but very little. So you get something that's super accurate. And in the limit, if we could somehow make the number of rectangles become infinite and each rectangle get infinitely skinny, in other words, have a width of 0, you would end up with the exact area. And as I said on the last page, the exact area is approximately that number that I wrote down, 15.08494467, and that decimal goes on really forever. But we can actually find the exact area not in decimal form. The exact area turns out to be 32 root 2 over 3. Of course, how do I know that? That's that magical theorem that we will learn about in the next section. So that you have to kind of wait to find out how I knew that. But yeah, we can find the exact area under the curve using this method of rectangles if in some beautiful ideal world we could break up this interval from 0 to 8 into an infinite number of rectangles, each of which has a width of 0, and somehow add up an infinite number of things. Okay, well, the next thing that I want us to do is to try to generalize this process. Okay, so how do we generalize this process? What we're going to try to do is now look at a general function y = f of x instead of our specific one, f of x equals root x. So we have a more general curve here, and I just drew a nice general curve. And instead of looking at the interval from 0 to 8, we'll be looking at the interval from a to b. I am going to make some assumptions about this function f on this interval from a to b. I'm going to assume that it's continuous. It turns out that actually all it needs to be is piecewise continuous. It can be discontinuous at a finite number of values between a and b, but for the time being, let's just go ahead and assume f is continuous, and we're going to assume that it's non-negative. I'm going to say f of x is greater than or equal to 0 on the interval from a to b. And remember what that means about the graph. For f of x to be greater than or equal to 0, it just means this black graph is above the x-axis, or if f of x equals 0, it may touch the x-axis, but it doesn't dip below the x-axis on this interval from a to b. And we'll worry about the situation where it dips below the x-axis on that interval later in the next section, so don't worry about that yet. So what we're trying to do is to generalize the process we just talked about creating these rectangles, so that we can estimate the exact area that would be under this curve y = f of x from a up to b. And so I've divided it now, instead of dividing it into a finite number of strips like 4 strips or 8 strips or 16 strips, I've divided it into n strips. And I've called each of the strips S1, S2, S3, and so on up to S sub n. So n strips. And if I want the width of each of these strips, remember we said to find the width, we just take the length of the entire interval, which would be b minus a. This endpoint minus this endpoint would be the length of the entire interval, and we divide by how many strips we've got. We're breaking it into n strips, so I divide it by n, and that will give me the equal width of each of these strips. So that is the width of those strips. So this is the length of the entire interval. We'll say entire interval from a to b, and This is just the number of rectangles. Number of rectangles. Okay, so let's go ahead also and label the x values for the right and left hand endpoints of each of these strips. So the way we usually do it in a general setting like this is we call A, whatever value you're starting at over here where your interval begins, your entire interval begins, we call that x sub 0. And then the next strip will begin at x sub 1. The next strip will begin at x sub 2 and so on. So we just label these with subscripts since we're looking at a general setting. The very last side of the strip, B, is going to end up being x sub n, the way that we've labeled things. What would this x value be that would be just below that? That would have to be one lower subscript. So if this is x sub n, this left-hand endpoint of the nth strip would have to be x sub n minus 1. So that would be the left-hand endpoint of this strip. This is the ith strip, strip s sub I. And if you want to, you can write down the x values for the right and left-hand endpoint of that as well. And it will start at x sub I minus 1 and go up to, this one would be x sub I. That's kind of a tiny picture there, so let's go to the next page where I have a bigger picture and it'll be a little bit easier to see those different subscripts. So I'll repeat that on the next page.